warm welcome to everyone, and you are watching the Maker FM podcast. Technology disruption will significantly impact the engineer of the future, requiring adaptability and mastering of emerging technologies. But those skills will have to be inculcated from the school, university level itself, because universities can play a key role in shaping future forward minds in India. What is it? Who is actually the engineer of the future? First, we have to know that. And to break it all down, please help me welcome Professor Timothy Gonsalves, founding director at IIT Mandi, who was there for about a decade, spanning 2010 to 2020. Professor, it is my sheer pleasure and privilege to welcome you to yet another meaningful episode of the Maker FM podcast. Someone like you who had such an illustrious career, you've been the founder, co-founder of several institutions and companies, you built Nilgiri Networks, IIT Mandi Catalyst, and so on. So I have to begin by asking you that what is it that really keeps you going?
Thank you for the introduction. I think what keeps me going is that there's a lot that needs to be changed in the world. A lot of people could be doing much better, a lot of injustice. And I want to, what keeps me going is trying to change the world. And I think I've always been aware of all the problems that we face. I'm also optimistic that change can be accomplished.
Thank you, Professor, for this and for laying this out so beautifully for us. In 2025 and beyond, what do you think with all these technology innovations constantly disrupting what we once thought to be the status quo? What does an engineer of the future look like?
As you very rightly pointed out, we are living in an era of rapid change, and the rate of change is increasing. When I studied engineering about nearly 40 years ago, it was assumed that what we studied at that time it was 5 years, would serve us for a 40-year career. That technology changed rather slowly. Now, what students learn in 4 years, if they're lucky, it will serve them for the next 4 years. But even that is not guaranteed. So I think the engineer of the future, who are students today, one is they need to be able to learn by themselves. They need to be self-motivated. They need to be able to learn on the job and also learn for their next job, because the job that they're doing might well become obsolete due to changes of technology. And we're seeing that. For instance, in 1990s, there was the Y2K problem, and India, in fact, became a major software power by solving the Y2K problem. After 2000, that problem disappeared, and people had to work on something different. Now we have people, everyone wants to work on machine learning and AI. In 5 years, those jobs may disappear. There may be something else that we have to work on. Secondly, as engineers, engineering depends on certain fundamentals of science, of technology, for instance, mathematics, computing, and so on. So whatever an engineer works in, he or she needs to be strong in these fundamentals. There are also professional skills such as teamwork, good communication. Again, these are essential and will always be essential. Because of the changes of technology and also the nature of when you work on an engineering product, it involves teamwork with people from different disciplines working together. So a good engineer needs to have breadth of knowledge and also be an expert in something. So both breadth and depth are required. The engineers solve problems of society, and they're useful because they do that. So a good engineer has to be able to find problems to work on. For instance, if I'm a programmer and my style of programming becomes obsolete, maybe I see that climate change is a big problem and I decide to work on climate change. Okay, so I have to be able to pick what are going to be the problems relevant for the next 5 years or 10 years. And finally, as I think you alluded to, a good engineer has to be willing to experiment, take risks, to fail, learn from the failures, and then succeed. So these are, I think, some of the characteristics I'd see of a good engineer of the future. Ability to learn, having strong fundamentals, ability to learn well, take risks, willing to change, and being able to work in teams across disciplines.
That is sort of very well laid out, Professor. So I have to ask you that you are seeing some of those skills in your interaction with students that they have had as you prepared engineers of the future. But if you were to sort of really identify what are the particular areas that they think that you think that they lack and they have to really build expertise on.
The traditional curriculum that the traditional engineering curriculum is sort of uh, a bottom-up type of approach. What it does is in the first year, uh, teach students the fundamentals of sciences, maths, physics, chemistry, and a little of engineering. In second year, they get into their branch. In third year, they begin to do some advanced work in their branch. And finally, in fourth year, they start to actually apply what they've learned in a project. Now, of course, by that time, most students are busy thinking about their jobs, or they've already got a job or higher studies and have lost interest in what they're doing in the college. Yeah, so what we did in IIT Mandi, starting from 2012, we introduced a new BTech curriculum in which students learn by doing, and they do real engineering type of work starting from first year onwards. Because one of the things that people may not appreciate is that engineering is not only science and technology, it's also a lot of common sense. And so with sufficient common sense and finding out learning on the job, one can actually develop useful products without advanced knowledge. So we take first year students, we have them work with real products. First, they dismantle existing products, such as a table fan or a mixie. They learn how it works, how to fix it, how to reassemble it, and how to improve it. A lot of engineering is improving on the previous version. Then we give them small, ask them to work on small, say, an automation, a small robotic device. And in a couple of days, it's possible nowadays to learn enough to actually build a robot that does something useful. For instance, it might detect when someone comes into a room and turn on a buzzer. That's a simple burglar alarm system. So students get the excitement that yes, they can actually do something useful. They have something physical that they can hold, and they can show to their grandmother and explain to her what it is. When you develop software, you can't do that. It's all something sitting in a computer that. Then in the second year, we ask students to actually work on uh, uh, to identify a problem in society. So in other words, find some potential customers, design some solution, build it and get it working within a matter of about 3 months. And with a limited budget, so they have to be frugal. They can use anything that they can buy in the market and build on it, but it must be within their budget. And at the end, there's an open house where essentially they're delivering a working prototype to the customer. Okay. In the third year, we have students going in greater depth into particular topics, but again, they learn the topic by making something useful, a potential product. And in fourth year, of course, students can spend the full semester or a year working on a major new product, which could even lead to a startup. So if you see in the entire 4 years, students go through the progression. They get a lot of hands-on experience, and they understand what a product company does. See, when developing a product, the first thing you do is understand the market, the state of the art, what products already exist. Then you see how can you improve it, make a prototype that is better. Then give that to a few customers, see whether they like it. Do they like your improvement or not? And if they do, then launch it at large scale. So students get this full experience in college. And after retiring from IIT Mandi, I started a program called LEAP, which is in partnership with Maker Bhavan Foundation, where we provide this type of content to students in engineering colleges, even in remote rural areas and low-ranked colleges, so that students can get the similar type of exposure to the real-world engineering that IIT Mandi and students in IIT Mandi and other IITs get today.
So, Professor, I have to ask you, suppose if we can, let's compare two students who took two different paths. Okay, so one followed the standard curriculum, the other one sort of deeply engaged with experiential learning. It was more collaborative and messy, where they had to engage with real world projects. 5 years down the line, how do you think their trajectories might diverge in terms of how they view the world, how they take risks, or the impact they make? What are your capacity predictions in this regard?
Taking first the student who goes through the traditional curriculum, memorizing material to do well in exams, that student most likely will not be in an engineering job after 5 years, because most companies that are looking for engineers find such people are not suitable for engineering jobs. So that person is likely to be perhaps in sales and marketing, maybe a delivery agent for some courier company, maybe just looking for a job, and perhaps doing some very routine maintenance in an engineering company. For instance, if an appliance at home breaks down, he might be sent to repair it, those kind of jobs. And the person who goes through the experiential learning, the IIT Mandi type of curriculum, uh, will very likely be working in an engineering team in a company that is making some state-of-the-art products, and not just routine manufacturing, but doing design of new products. That person is likely to, in 5 years, to be leading a small team in design. That person is on a fast technical track. It's quite likely that she has also decided to start her own company and is an entrepreneur. Some people who go through this experiential learning of taking problems of society and trying to solve them realize that the solution is not purely engineering. So some of them might decide to either start or join an NGO, or maybe go into civil services and solve problems of society from with a combination of technology and other aspects. In whatever way, I think this second person, the person taking the experiential track, will be on a fast track to becoming a leader in whatever field she goes into. Just to give you an anecdotal evidence, we started LEAP about in 2021, and we offered it in a college in southern Tamil Nadu. Some students in the second year, about 50 students, took the LEAP program where they designed their own products and built them and got them working. These students are among 400 students from that college who graduated in 2024. And we did a survey recently to see what the students are doing. And we found that among the 50 students who did the LEAP program, the placement, about 81% are placed. So in 2024, placement was a bit
Wow,
poor.
incredible.
For the college as a whole, the number placed was 47%. So it was almost the students who went through and this was, they did experiential learning for just one semester, not for 4 years. So you can imagine that those who go through a full 4 years would do much better.
Definitely, there are nuances to it, but you beautifully explained this, Professor. I must tell you, if you had to dissect the everyday engineering curriculum a typical learner might have to engage with, where are the areas where you see the mismatch between what their current skills, thinking, and problem solving ability is versus what the real world readiness should look like? What elements of the traditional academic approach do you think is failing or even retarding students?
I think partly I'd answered that question earlier when I talked about the need for students to learn by doing, and also for the students to pose the questions rather than having the teacher pose the questions. And also, a significant part of the problem is the need for that at the time of graduation, employers and others want some marks. Each student should be. So essentially, they're asking colleges and the universities not only to educate the students but also to evaluate and rank them, so that it makes it easier for the employer to select from a large pool. So, uh, so one of the uh, problems of the education system is that it is geared towards teaching students how to answer questions in an exam and how to get good marks, which is not what see, an engineer needs to figure out how to make something that works and which the customer is willing to pay for, and to do it within a before the customer gets tired and goes and buys someone else's product. So it has to be done within a time frame. It has to be within the cost. It also has to conform to laws and regulations, and it has to use the existing technology and materials. See, scientists may work on something that becomes practical 100 years from now. An engineer has to work on something that will be delivered 3 months from now. So, so that is the difference. And the way of teaching does not bring in any of this. Also, if you look at the traditional way of teaching, the theory comes first and then the lab comes after that. So that often the lab is some routine experiments which just confirm what the student has already learned in the theory. For instance, some students in IIT complained to me that the physics lab is boring, the first year physics lab, because they said they do about 9 experiments in which they measure the value of g. G is the acceleration due to gravity. And they've already learned in theory that the acceleration due to gravity is 9.80665 meters squared per second. So why should they spend one semester confirming that in the lab? Now, on the other hand, supposing the students were let loose in the lab before they learned about this acceleration due to gravity, which is a constant throughout the world, and they were told, okay, play around with drop some objects, drop a ball, drop some other things, and what can you learn from that? Now, it's quite likely that they might figure out that, yes, there is some constant acceleration due to gravity. So they actually will figure out the theory. Then when they take the theory course, they'll, of course, get a much deeper understanding. So, so that is one of the innovations that we have done in the curriculum, namely to flip the order of theory and practice. Have the practice come first, so that students learn some of the theory on their own out of need, because they have to use it in order to get something working. And then later on, they can go in greater depth into theory.
This sounds very fascinating. Let the practice come first and the theory come later, as you said. So maybe there are institutions that might actually tout project based learning, but it might be that they're just doling out assignments divorced from the real world to tick a box, and it actually may be something called an innovation wash. What are aspects of a project that you think would make it truly transformative or meaningful for a student to change the way they look at an idea?
See, the goal of an engineering 4-year BTech should be to make the students start to think like an engineer. There's we hear about scientific mindset and uh, uh, design thinking and other things. There is this concept called engineering thinking. Now, how does an engineer think? The first thing an engineer does is to look for problems around himself or herself and try to fix them. For instance, using technology. For instance, at the beginning of this call, you were telling me that my video didn't look quite right. It was too narrow or slanted and so on. and then I manually adjusted the camera and got everything fixed. Now, that's a problem that you'd face, I'm sure, when you start each interview. Now, an engineer will say, okay, can I devise something to fix this problem automatically? So that the interviewer doesn't have to spend a couple of minutes with the interviewee at the beginning. So that is the way an engineer thinks. Just if you're sitting in a restaurant, you look around and see what all are the problems. Okay, these tables are slightly too close together. Then maybe should the tables be made smaller or should the room be made bigger? An engineer is always asking questions like that. A non-engineer would say, is this dosa fried properly? Is the chutney too spicy and so on? That is part of engineering thinking. And again, when you talked about this having project-based learning, where in many colleges, what is done is that the problem that the students work on is given by the teacher, and then all the students in the class will work on the same problem. And of course, there may be the sort of standard solutions that the teacher expects. So as you said, it's more to tick a box. Now, for true project-based learning, what is done is that the students are asked to come up with a problem. So each team of students may come up with a different problem. And we may give them some theme. Say you come up with problems for precision agriculture or for healthcare or something like that. But they come up with different problems. And of course, each solution will be unique. So they are finding the problem, they're devising the solution. And then the students also need to learn to work within constraints that, for instance, typically in the engineering curriculum, each course is taught independently by itself. They need to be able to tie all their courses together and say, how do I use knowledge from different courses to solve this problem? Okay. And finally, the proof of the pudding for a product is will the customer buy it? So in any useful project-based learning, there has to be something that mimics delivery to a customer. For instance, it might be that there's an open house where anyone can come and make comments and give feedback, and that is used for the evaluation of the project, not just some experts who do it. Or it might be that the students are asked to go out into society, talk to potential customers and get their feedback and record that and report that. So the true project-based learning should inculcate this art of engineering thinking, of thinking like an engineer into the student rather than thinking like a student who studies something to get marks or out of curiosity or academic interest.
I really like that expression, the art of engineering thinking. So, how does one define what is a good problem to solve? What is an average problem to solve for that matter? Do you always have to go back to the drawing board to keep iterating till the time you sort of get it correct? Is that the way innovation works, the design thinking works? How do I assess the problem that I've taken on myself to solve for is worth pursuing in the first place?
So that's a very good question, and to some extent, it helps to differentiate engineers from scientists. A scientist will work on a problem until he understands it completely and thoroughly, and will then publish a paper on it. An engineer will figure out and work, solve the problem to a sufficient extent that she has something useful that people can actually buy. It's not perfect, but it's useful. So so that's often called a minimum viable product. It's something, and you see that in, for instance, cell phones. Today, if you're using an Apple or Samsung phone, what is the current version? Something like 15 or 16. And back when they introduced iPhone 1, they told you this was the perfect iPhone. You bought it, and 1 year later, they told you that, well, now we actually have iPhone 2, which is solves all the problems of iPhone 1, and so on. So that's how engineering works. That it, people have to iterate. Now, as to how to figure out which problems to work on, which are good solutions. Their experience is important. Experience plays a role, and students get experience by playing around. And in fact, that's where things like the Maker Bhavan sets up tinkering labs in colleges where students are free right from first year to go any time of the day or night and work on anything they want to. So they can tinker around and they can fail. Then after a year or two of failures, they start to succeed. So then they begin to get an idea of what is worth working on and what is not worth working on. Like, and the same applies to selecting problems. That if there are many problems in, say, the restaurant, in the lighting and the design of the tables and chairs and so on. Now, which one do you work on? So there's some common sense is required, and that comes from experience. You say that, okay, I have expertise in this area, and from what I've spoken to, people are upset about something. So if I solve that problem, they'll be more willing to pay for my solution.
There's a combination of common sense, logic, experience, and perhaps some degree of intuition.
One thing I'd like to add is that although we say that students can do engineering right in first year, of course the level of engineering is becomes better and better as one gets more experience. There is a general rule of thumb that if you want to become an expert, one of the leading experts in the world in almost anything, it takes about 10,000 hours of effort. And if you look at a 4-year BTech, a student who works hard spends about 8 to 10,000 hours. A PhD for 4 to 5 years, again, someone spends about 10,000 hours. So, so taking a course, say a one semester course on innovation, will not make one an expert on innovation. It requires working working on a number of different ideas, and that's why in LEAP and Make Above One Foundation programs, we start out with students in first year, so that over the 4-year period, through the tinkering and leap courses as well as the academic curriculum taken all together, they can become expert engineers.
Thanks for reiterating this. So, we have to be true and honest to what we are pursuing, and we have to give that kind of time and energy and resources to it, right? Like you said, that 10,000 hours you will have to put, no sort of shortcut to be an expert over anything. You have to put that required amount of energy.
Yeah, that again comes to one of the very important problems, namely the fact that in India, most faculty members are teaching engineers to work in industry, and the teachers have never worked in industry themselves, by and large. Now, just to take an example, Germany is well known for excellence in engineering. Mercedes-Benz and almost anything you name, Germans are leaders in that. And one reason is that to become a professor in a German university, one has to typically have about 5 to 10 years industry experience, in addition to the publications and academic record and so on. In India, we don't have that. So, so the question is, how do we uh, help incentivize faculty who don't have industry experience to get some industry exposure so that they can then mentor students in this. So there are several things that can be done. What we do for instance, in the LEAP program is that before we run any program for students in a college, we first run a faculty development program to train the faculty in the practical methods. And we have the faculty themselves working on hands-on projects, including dismantling mixies and building automation devices and so on. And I can tell you that for many of them, this is the first time that they've done something useful with their hands. And pretty much they all love it. They all get quite excited by that. And they're now, after this, for them to spend time mentoring students, it takes time. And in most colleges, faculty are quite heavily loaded with teaching duties, lab duties, administration, and so on and so forth. And so the management needs to show them that their work on incentivizing project-based learning, mentoring project-based learning is recognized. And the way it should be recognized, one is typically in private colleges, every year there's an annual appraisal which determines their salary increase, and it's often based on some points. So the mentoring of students in projects should also get sufficient points. When looking at the workload allotment by the head of the department, typically it's only the teaching which is considered. So this kind of mentoring should also be considered. At the time of promotion, it should be considered. And likewise, the college should put ongoing efforts into inviting people from industry to come and have interactions, maybe have an industry conclave, encourage faculty to perhaps go and visit industry during their vacation period. So the message should come from the management in tangible ways that this is considered a valuable contribution.
Thank you for that, Professor. You made some very, very pertinent points that you have highlighted in terms of incentivizing, promotion, faculty development program, things like that. We're sort of getting towards the end of this very, very meaningful conversation. We spoke about various aspects in terms of what does the engineer of the future look like, how does it differ from an ordinary mindset, problem solving, and really what is the real world readiness and what are the kind of skills are required there. So, Professor, I have to ask you perhaps like my last question on over the course of this podcast that we've interacted with three professors. There was one aspect that kept on coming was basically about the cross-pollination of ideas, that you can't really be siloed if you have to really become the engineer of the future. So I want to understand from you that how do you get different teams and team them together? Is there a case to be made that engaging with humanities subjects might make for a well rounded engineer?
Yeah. Yeah. So there are actually sides to your question. One is that in an engineering team, the engineering is the product is typically developed by engineers from different disciplines.
Mm-hmm.
Students from, say, computer science need to be able to understand something about mechanical engineering and about electronics and so on. For instance, if you take something like, say, a cell phone, there's quite a lot of software in it. And there's also the hardware, some mechanical parts. There's plastic and other materials. There's a lot of electronics. So there needs to be cross-pollination of ideas, teamwork among engineers from different disciplines. Now, bringing in the humanities, again, if you take the same cell phone, one of the things that we do with it is that we post things, we take photos and share the photos and share things about ourselves. Now, do people worry about privacy? And what is the concern about privacy? Is it different in India, in Europe, and in the US, in different societies? So these are questions that are crucial to designing a cell phone that is used. And these are questions that, for instance, maybe psychologists would understand. An engineer may not understand it. Likewise, how do you have, say, social media groups which are formed, which again drive the use of this cell phone, so that perhaps sociologists understand. And then, of course, there is the pricing of when you sell a cell phone, do you sell it by if you remember originally, I don't know, maybe before you were born, since you're quite much younger than I am, people had telephones, wired telephones. Yeah. And at that time, you paid for the telephone connection, and the telephone was given free by the operator as part of the connection. Now we buy the telephone ourselves. And so this has been a shift in the economics of telecom operators. So that kind of shift took place in part because of, say, economists and other people who figured out that this was an easier way of running the business. So yes, there is a strong case for humanities to be involved. Again, the engineer doesn't have to be an expert psychologist, sociologist, economist. But the engineer has to be able to talk to such people, has to be able to understand how those people think, the language that they use, the jargon that they use, and vice versa. So in the IITs, we've always had some amount of humanities in the BTech program. In IIT Mandi, we increased it in our BTech program, where students would do a minimum of 12% of humanities courses, and they could take up to about 20% of humanities courses. So, yes, I think there is a strong case for a good engineer needs to be aware of the wider world beyond technology and science, and therefore needs a strong grounding in humanities also. I think the students of today who go through project-based learning for 4 years spend their 8,000 or 10,000 hours on it and become really good at it, including learning some humanities, they can become the people who conceive those products of the future that are widely used and which make a better life for many people.
It was my sheer pleasure and privilege to have you, Professor, as part of this conversation. Thank you for your time and energy to the Maker FM podcast. And for our viewers and listeners, till the time we see you next, goodbye and good luck. Thank you so much.